Hello everyone, this is Mr. Jackson, and today we are going to be concluding not just our Concept 3 on the muscular system, but we're also going to be wrapping up all of Unit 2 with this final part of the discussion. And so this will be Part 4, the last little part that goes along with your muscular system. We want to make sure that we understand the whole point of knowing the ins and outs of muscular contraction is ultimately based on their ability to create movement, or otherwise stated, their ability to create force of movement so that we can move and navigate our surroundings and also manipulate our surroundings, such as lifting things up, for example. And so we want to get right into it. Whenever we're referring to force, muscles can increase the overall amount of force that they create in a few different ways. They can increase this by increasing the overall frequency, so how often those motor neurons are being stimulated. So this basically means that your individual little sarcomeres, all in a row, they're unable to actually relax, so they'll actually stay contracted because you're constantly keeping them stimulated, right? So the more frequent the stimulation, the more powerful those contractions will be. You can also increase the number of overall motor units. Basically, a motor unit is just the nerve fiber, so that somatic motor neuron, however many muscle fibers it innervates. That is what we refer to as a single motor unit. Okay, it's just one unit, the nerve plus all the fibers that contract because of that nerve. And so we can increase the overall force by increasing the number of those motor units that are stimulated, right? So more sarcomeres being contracted, more overall force of the contraction. And then also you can increase the size, the overall size of the muscle fibers. So it's basic, the bulkier the muscle, the more tension that can be built inside that muscle. And again, this is all about how many of those sarcomeres, how many of those myosin and actin cross bridges are able to be recruited, are able to be stimulated and then contracted. So again, we can increase force that we can create by increasing the frequency of how often these sarcomeres are stimulated, by increasing the overall number of sarcomeres that are stimulated, or increasing the size of the sarcomeres that are stimulated. But then we have one last way, one last lens that we want to look through in order to understand how we can create an advantage and be able to manipulate and to use our muscles as lever systems. And this is where we get into just a little bit of physics. So muscles act with bones, and the way in which these muscles and bones interact essentially create, from a physics lens, levers. They create a variety of lever systems. The bones themselves, so you can see here, the bones themselves, this could resemble a bone, those act as levers. The joints, somewhere along where those two bones meet, act as what we call a fulcrum or an axis. And so a lever, whenever we refer to a lever, this is referring to some rigid bar that moves on a fixed point, a bone that moves relative to a joint when a force is applied to it. And that force that's applied to it, that effort that has to be applied, is always referring to the action of a muscle. Okay, so muscle contractions create the force or create the effort that can then be applied in order to move some sort of a load. Now, usually this could just be the weight of another body part, right? Because it's not weightless. You do have mass in all of the parts of your body. So if I were to be just basically raising my hand by completing elbow flexion, well, then the load is just the weight of my forearm and hand. But sometimes we're going to be holding things, might be like a gallon of milk, or could be a box or something of that sort. And that could also pose a resistance, a load that we have to create force to overcome. And so if the effort, you can see here in these two examples to the side, if the effort that you apply with your muscle relative to the joint if it's further from that fulcrum, if it's further from the joint, then this lever creates a mechanical advantage, okay? So the more distance that you have between where the muscle is pulling and where the joint is located, the easier it will be to actually create that movement. But if the effort via your muscle pulling on a bone, if the effort is closer to where that joint is, there's less distance between the two. That will create what we call a mechanical disadvantage, meaning if this is the same amount of effort and the same amount of load, it will be much easier for this muscle to lift that load than it would be for this muscle to lift that load, okay? And so we call each of these bones relative to the joint, we call these lever arms, right? So the left arm here would be much shorter than the right arm. The right arm has an advantage. If you look down at this example, the left arm, where that resistance or load is, much longer arm. The longer arm has the advantage. And so that's the easy way to think of these things. We have a variety of these in our bodies, and we're going to go into 3 different examples for how these 3 factors are arranged in your body. Okay, we have what is called a first class lever. Okay, so we're going to go through first class, second class, and third class. First class levers, you can see them here. Okay, same example, it's going to be these 3 things. Okay, you're always going to have a load, the fulcrum, which is the joint, and the effort being made or the force applied using your muscles. Okay, so in a first class lever, the effort is applied at one end of the lever, and the load is at the other end, and the fulcrum is somewhere in between. This is like a seesaw. That'd be a really good common example. A seesaw would be a good example. You can see an anatomical example here at your cervical spine, where basically in order to extend your cervical spine, you have to apply a downward force posteriorly so that at this fulcrum, at this joint, your chin can then be raised. You have another example here of what this might look like if I were holding a long stick. The force applied, so I would push down, and then I might be able to then flip this load or flip this rock, right? And so the further that I get away from that joint or that fulcrum point, the more advantage that I'll have, okay? So again, the anatomical example is just that same lever system that raises your head from your chest. That's that cervical extension. And then the big thing here is you want to know that you have the fulcrum or the joint in the middle. The load is on one side, and the force you're applying is on the opposite side of that joint. Okay, so that's a first class lever. Okay, so load, fulcrum, and force. A second class lever is where you're going to have that effort via your muscle. It's going to be applied at one end of the lever, and the fulcrum is going to be all the way down at the other end, but the load that you're actually trying to manipulate or lift is going to be in the middle. Okay, so now rather than it being load and then fulcrum and then your effort like it was in first class, now we've got the fulcrum, then your load, and your effort. Okay, so this is very similar to the way that a wheelbarrow works, where your fulcrum is the wheel, right? That's that joint or that axis. The load is whatever's in the wheelbarrow, and then the force that you have to apply is there at the handle. Okay. You also have an anatomical example, which is whenever you complete what we call plantar flexion and you lift up onto your toes, the balls of your feet and your toes, they serve as that joint. They serve as that axis, that fulcrum. The load is going to be the weight overall, the weight of your body pushing down. And then the applied force is going to be your calf muscles, right? Your gastrocnemius and your soleus muscles that have to, on the other side of that load, opposite of your fulcrum, going to have to apply an effort or a force. Okay, so that's a second class lever. Again, the big thing to take away from this is where are each of these 3 factors, right? So you're always going to have your fulcrum that resembles a joint. You're always going to have an effort, which is your muscle's action, and then you're always going to have a load, so something in terms of resistance that your body has to overcome in order to create that movement. Okay? And then finally, last slide of Unit 2, last slide of this conversation is going to be a third class lever system. So this is the last type of lever. Third class lever, it's again, a different arrangement of those three factors. This is where the effort that you're applying is going to now be in the middle, okay? And it's between the load that you're trying to overcome and the fulcrum. This could be like the way that tweezers are set up, forceps are set up this way, catapults, like you see here in this lower left image right here, catapults work this way, where basically the force is going to be in between the load that you're trying to send or catapult, and it's going to be about this fulcrum here, that axis. An anatomical example, a good one, would be the way that your body works to complete like a bicep curl, right? Very common example we use in anatomy and physiology, where you have your elbow as the fulcrum, as that joint. You're holding a load in your hand, and on the other side of that joint, you have the actual force that's applied. But the thing that you want to keep in mind is, even though it looks like this force is on the opposite side, look at where this muscle, the biceps brachii, look at where it's actually attaching. It's actually attaching closer to the load than it is to that joint. And so while we might think like, oh, the muscle is on the other side of the elbow, not if you consider where that insertion point is, where one of those bony attachments are that actually will pull on that bone to create that movement. Okay, so I think that is more than enough to go off of for our purposes for this unit. I hope that you found this information helpful, and we will see you at the next one.